Alrighty, welcome to the next part in our motor-driven roller project. Here we're going to, so last part we just modeled these custom 3D printed pulley end caps for our rollers. What we're going to do now is we need to start kind of fleshing out this assembly, and we need to model some components that depend on the geometry of the assembly. So we're gonna go ahead and build out the assembly here, and then we'll model the parts that we need after that. So let's rename this. Okay, all right. So then let's go ahead and insert the. We might as well just insert the entire part studio, and then we're gonna ground. We're gonna ground this plate, fix the plate. Sorry, and then we're going to group. I'm gonna group this belt, the pulleys, and these two parts, but I'm going to leave the motor belt out of the group because the motor belt's actually going to go over here on this side. So I'm going to do that and then group those. And now none of these should move. So we fixed this plate so it can't move, and then all the other ones are grouped with it so they can't move either. So that's good. All right, so then what we need is we need to copy this plate. I'm just going to Control C, Control V, and then I'm going to do a fasten mate there to there, like that, and it should keep the same orientation. All right, so then that's basically the arrangement there. So then what we're going to do is we need to put in our bearings and our motor. So I'm going to just use MKCAD for this. My favorites, bearings. We should actually favorite some of these. So half-inch thunder hex. Oh, I struggle to find this bearing. Oh, it's all at the bottom. Okay. Flanged and radial. So I'm going to favorite that. Put this guy in there. Okay, so we need that guy, and then I'm going to just go and drop some other components in. We need two of these. So I'm going to copy paste, and then motors. Neo. I'm actually going to check. I believe the Rev website has a better model up. I need to check though. Not yet. Okay, so I'll just use the MKCAD one then. Neo brushless. It's okay. And then let's see, what else do we need? We're good on bearings then. I don't think they have needle bearings in here at all. We're gonna have to import all that stuff, so that should be everything we need from MKCAD. Oh, nope, I lied. We need the pulley. I believe it's here. It's a 16 tooth. That's the Vex one. 8mm bore. Yeah, it's this guy. All right. Okay, so now we've got all the components. So let's go ahead and hit M for the fasten mate, and let's just go ahead and mate the bearings where they're supposed to go. Flip them around so the flange is inwards. We are actually going to go ahead and add a bearing retention feature for these. I think I'll explain kind of why you do that and how that works a little later. But there's going to be more that we're going to do with the bearings in a little bit. Also keep in mind, because these plates are not actually a 1/4 inch thick, they're 0.22 roughly, the bearing will stick out on the back side. So if you're designing with 1/4 inch polycarb, just keep in mind that this bearing will not be flush like it would be if you were using like 1/4 inch aluminum. So that's something to keep in mind. All right, let's see here. What we can do before we constrain the motor, let's constrain the pulley to the motor like that. We may add some space here, but for now I'm just going to stick it all the way on like that. This is how it's designed to work, but you can space it out a little bit if you need to. And then I'm gonna do make connector to this guy. Come on. And then flip that around. And then what we actually need to do is this needs to be spaced out and then needs to be rotated a bit so the holes line up. So I'm just going to do that with the offset. I could make this a revolute or something and then do other constraints, but I'm not going to bother with that. So I'm going to do like a, oops, some sort of spacing here. We'll adjust the spacing a little later once we get the other pulley in here, but I'm going to just start with an inch. And then we want to rotate around Z. And I want to put the wires facing straight up, and then that will make the holes line up. So I need to go 135 minus 135. There we go. And you'll notice the mounting holes line up now as well. Okay, so then we're good there. That's as much as we need to do on the motor. And then, so what's going to happen is this front roller is not going to have a belt, a pulley over here. We're going to need to design another end cap that just goes here that just holds the bearing and doesn't do anything else. That'll be pretty easy, so we'll do that in a little bit. However, the motor is going to drive a pulley here. Now this pulley here is just going to be the same end cap that we have over here. So I'm just going to select this, just copy and paste, and then all we're going to just do is just constrain this to the bearing, like so. And the hex is upright. Yeah, okay. The hex orientation being the same doesn't actually matter. I just wanted to make sure it was, just because it's a little cleaner. Okay, and then this belt over here is it just needs to be constrained in place. Now, the thing to understand is we've got these mate connectors already positioned, and they're right in the middle of the belt, left to right, so that's nice. The thing to understand over here is that the tips of each of these teeth are actually a portion of a cylindrical surface. And if we select this cylindrical surface, we can get a mate connector that is centered in the cylinder and on the center line of the cylinder. So that will help us constrain this belt properly. So if we select this mate connector here, and then we zoom in to one of these faces, and we kind of just go into the middle somewhere where we're not selecting. We don't want to be like selecting one of these corners or anything. We want to be kind of in the middle. And you can see how the mate connector jumps to this like weird spot over here. That's because it's in the middle of the cylinder. So if we just select this, we just click, the belt goes right in the middle of that pulley, just like it should. And then it is just kind of positioned over here, you know, wherever it falls on this pulley. So that is just what we want. And then because the belt was modeled in the correct orientation, like it was modeled in this correct like horizontal orientation, the orientation will be correct when it's constrained over here. If it was modeled like vertically or something, we would have to reorient it over here to get it to line up on this side. But because we modeled it kind of in place, it's all correct. All right, so then I think we're actually done with all these mate connectors now. So I'm just gonna right click on a mate connector and just hit hide all mate connectors just to get them out of our way. This spacing here looks pretty good. The motor shaft does stick out a bit. Depending on what this mechanism is and what you're doing with it, this might be a problem or it might be okay. It's sticking out by, you know, about 4 millimeters. So, you know, depending on what you're doing, this might be a problem. Obviously, we've got this big clearance hole here to clear the pulley. That helps for assembly as well. So I'm just going to leave this alone. 1 inch spacing is a nice round number. We could go, we could go even less spacing just because we've got this big gap between the belt. The belt can go, you know, closer to the motor if it needs to. So if for some reason this motor was sticking out too far and interfering with something here in the middle, you know, maybe you'd want to move the motor outwards a little bit, and you have the room to do that. So for now, I'm just going to leave the motor where it is because we don't have a defined like location it needs to be in. However, that's an option as well to understand. Okay, so then what we need to do here, we need to model the standoffs, we need to model this end cap here, and we need to model the actual roller tubes that go across here. So we're going to go ahead and do all of that now. So let's do this. We're going to use a context to do this, and I think we're going to just base the context off of this part here. So I'm just going to right click on this and hit edit in context. So we get this context here. We've got this kind of the ghost versions of all these parts. So let's go ahead and just start with the end cap because that's kind of the biggest component that we need to have. So this gap is 330 or 1/32, and we're going to make sure we do the gap the same way over here. So we know I already have a plane that cuts this end cap kind of in half that we use to do this flange. So I'm just going to use that. I'm just going to use that plane again. Just believe this plane. Yep. I'm going to create another sketch on that. And then I'm just going to use that plane to create the end cap over here. And then we're just going to revolve it. So let's just create some lines. So this will be clearance diameter. This will be bearing. Then we're going to have some sort of a flange that just holds the polycarb tube on, and then we'll do this, and we'll probably just do, actually, no, I don't want to build the chamfer into the sketch. That would be kind of annoying to deal with. So, all right, so then, all right, so, and then I'm going to select this and project that line. That just gives me kind of a reference point, and then I guess I'm just going to do this as well. That can be vertical, and then these two lines, actually all three of these lines should be construction. This represents the center line. Obviously, I just attached it to the midpoint of this line over here. All right, so the distance between here and here, that wants to be 0.03125. And then this here, oops, this here wants to be 1/8 diameter. Now, here's a little trick. I don't remember if I've showed this before, but if I do a dimension between a construction line and a standard line like this, and I put the text here, I'm just dimensioning the distance between them. However, if I move the text to the other side, it treats the construction line as a center line. You notice the attachment point for the other side of this dimension is changing to this like spot floating out in here in space. Basically, you'll notice it also adds the little diameter symbol in front of the numbers here that's right behind my mouse. Basically, it's anytime you dimension to a construction line like this, it treats it as a center, the construction line as a center line. And you can dimension by the diameter, which is a very convenient feature for doing stuff like what we're doing here. So we did, if I remember correctly, we did 0.675 for that. And then this to this should be 16th. And then I think this probably only needs to be like an 1/8 inch thick just to give it some meat. And then here to here was 13 16ths, 8125. And then this was, oops, that was 0.5 inches. And this was 0.75. Okay, pretty straightforward. All right, so then we can do a revolve. And it needs the axis. We can use this, or we could use the tube. Either way, it doesn't matter. That's fine. Okay, and then it's doing a new part, which is good. And then we need our chamfer. And I think we're probably fine on this flange. I don't need any chamfers or anything. Okay, so then what we're gonna do now is actually I should rename this. I'm actually going to give these pulleys names as well. I want them to be numbered. I don't want them to have the like, because they're both named the same thing right now, which is confusing. So I'm going to rename these and just give them part numbers. Just sequentially. The belts, though, I'm going to leave unpart numbered because they're not actually custom parts. Actually, what I should do is go in and put the rev part number and the vex part number in the name, just to make it a little easier to recognize what they are. Okay, so I'm just going to number all these, then I'm actually going to select these because I don't think they have materials defined. Oh, that's interesting. The belt calculator feature automatically adds onyx. That's interesting. Okay, I'm just gonna define them as this glass filled nylon though, just so they're all the same. It's close enough. And then edit the appearance and make it this dark gray. Okay, that's pretty good. All right, and now what we need to do is we need to model these standoffs. So these are pretty straightforward, although the only thing I'm noticing here is this standoff actually can't be here because this interferes with the belt. When we originally positioned the standoff, it was going to be uh, a 24 tooth pulley, and so this position wouldn't have been an issue, but now it is, so we have to move it. So we have two choices. We can either change the outside shape of this part so that there's some space up here where we can kind of jog out, grab this standoff, and then come back in, or we can move it inwards and put it inside the belt. I really don't like putting it inside the belt like that because then you've got to remove that standoff in order to replace the belt, and it's just annoying. So we're going to go ahead and change the outside shape of this. On this side, though, because this belt here, you have this belt reduction, this 16 to 30 reduction, this belt's on an angle, and so I think we're okay. We're not going to have any interferences with this guy, and we definitely don't have any interferences here. Okay, so let's go ahead and let's exit out of this context real quick, and then let's go to the sketch, and let's delete this dimension here. And here's what we'll do. We'll do a 3-point arc here. You'll see why I'm doing this here in a second. And then what we're going to do is we're going to cut this line segment out. And then these two lines, because I did the cut, these two lines used to be one line. Now they're two lines. But when you do the cut, it automatically adds some constraints between these two lines that we now have to delete. So let's hover over this line. Let's see what it's constrained to. So it has a coincident constraint to the other line, which needs to go. And then it also has a tangent to this circle down here, which is fine. But it also has a tangent to that top one, which needs to go. And then this line here doesn't have any constraints. So this line here needs a constraint added to this circle, a tangent. And then we also need this to be tangent to that. Oops, I shouldn't have done that. Control Z, drag this up at an angle. This will make the tangent work better. Move that down. Tangent there to there, tangent there to there, and then this and this should be concentric. Okay, and then we can just dimension the radius of this to be probably 0.25, and that basically puts us back where we were. Okay, so then the only thing we need to do here is define, kind of what distance we want away from the center line. So probably do from here to here, and then make this construction so it's not causing any problems. And then we can just define the distance from that to that. So we know that the pulley is smaller than 1 1/4. So, and it's okay for the standoff to be pretty close to this belt. So we'll do 1.25 divided by 2. We know the belt. We know the belt is smaller than 1.25 because we had to extend that flange outwards on our end caps, and that flange is flush with the top of the belt. And so because we had to extend that flange outwards to be flush with the tube, we know that 1.25 tube is bigger than the belt. So we can just use that as kind of a safe dimension. So that looks okay to me. So click OK. Hopefully everything rebuilds. Yeah, and because we didn't add any new regions or anything like profiles or anything with this, because of the way that we did this with adding the arc and then cutting it and all that stuff, this just works. We don't have any errors. It just works. Okay. So then let's go back to the assembly. Actually, no. Go to. Oh, we didn't actually make any changes in the context, I don't think. Wait, why doesn't my context not show up? Can I just edit in context? That's very strange. I wonder if I have something hidden. Weird. Yeah, usually the context appears up here at the top, but that's not the case anymore. So I'll have to look into that. Either way, we just hit edit in context again. That gets us back to where we want to go. So create a sketch on this surface here, and create. So this is an extrusion that we buy usually. So oh, actually, what am I doing? I don't want to sketch. There's a tool for this. So I want to just do this. The spacer should be good enough. Oh, I don't remember which one it is. I think I want spacer round. Oh, maybe it is the shaft generator. Does this have the round stuff? Oh, it doesn't. Okay, never mind. I would do want an extrusion then. Okay, so there's some tubing. I think you can buy it on McMaster. I think you can get it elsewhere, but if you do, it's 3/8 OD. Oops. Nope. 3/8 OD. Oh gosh. Uncheck that. There we go. And if you can get see if I can find it here. Not seeing it. Looking through the IDs. These are all super. Oh, here we go. It's this tube. So this 0.145 is the tap drill diameter for 1032 is 0.159. And so this 145 is super, super close to that 159. And so you can either, sometimes you can just force a tap into this and it'll just work. Or you can just really quickly take a 159 drill this out just by hand. And you can just buy this and cut this to length. And obviously it's 8 feet for $13. The price is pretty good. It's 6063, so it's not like super strong stuff. But we use this a lot for just like really some of these really long standoffs that we just need and just for some structural stability. So this is kind of a good trick, and we're just gonna use that here. So I'm basically just gonna model a piece of that tube, and then we'll just kind of imply in the CAD that it's tapped. There's nothing in the feature tree that we're gonna add to tap the hole, but you would make a note on the drawing or just whoever's making the part would just understand that it needs to be tapped just based on looking at the assembly. Some of these little tricks and things in FRC, it's the team knows how this stuff is built, and so sometimes you don't have to make notes of this stuff on the drawings because people just know the way that it's supposed to be built. In an actual engineering environment, obviously that's a very bad practice. You would never want to do that. However, in an FRC context, that's a totally acceptable way to do things just because it saves you a lot of time. Anything that saves you time in FRC is probably a good thing to do. Obviously you have to weigh the benefits in terms of cost and reliability and difficulty and all this stuff, but like generally speaking in FRC, the most limited resource is time above all else, not necessarily expertise or money. In a lot of cases, it's usually time that ends up hurting you. So we'll do this extrusion here. I just made it 145, and then it would need to get drilled out to 159, like I mentioned, or you just have to try to shove a tap in there. That can work with limited success. This should be a new part. It should be up to face. It should just be over there like that. And then I'm gonna rename this to 6, and then the material for this should be, I don't remember if they have 66. They don't have 6063, which is a weird material to be missing because it's like the most common like aluminum alloy on the planet as far as I'm aware. So light gray for aluminum. Okay, so that's good to go. And yeah, the context is showing up now for some reason, which is very strange. Okay, all right, so then the other thing that we need to do is model the tubes. However, I actually want a different context for that because I need, actually, no, I guess I don't need a different context for that. Okay, so we'll go and model the tubes now then. And then this standoff can be used in all 3 locations. So let's Let's just create a sketch here. And it's just going to be, I'm going to go ahead and model the tube, even though this is 1 1/8 and this here is 1 1/4, which are the two diameters we need. I could just project those two circles. I don't want to actually tie the tube geometry to the end cap geometry, because in the future I might come back and change the diameter of this flange, or change, make this slightly oversized for a more press fit or whatever, right? I might change this, and I don't want the geometry of the tube does not depend on the geometry of the end cap, and so I don't want to actually link those two together. So I'm just going to make them concentric, but I'm just going to actually type in the dimensions for these two circles, because those dimensions are actually defined by the tubing we actually buy rather than our design. Okay, so then I'm going to do extrusion. It's going to be a new part. I'm going to do up to face, and then it's just going to be up to this other flange over here. Easy enough. And then I'm going to do the same thing here, except I'm going to do up to face to this like ghost pulley. This is the reason to do this in context, because now I don't need to calculate what the width is. I just let the feature define it. Okay, so then I'm going to go here. I'm going to do the same sketch. Once again, not going to tie the geometry to, I'm going to make it concentric, but I'm not going to tie the size of these circles to the geometry of the end cap. So once again, new part, up to face, and that's the face right there. Okay, it's good to go. Starting to look like a thing here. All right, so then let's just give these part numbers real fast, and then select both of these, assign material, polycarbonate, and then I'm actually going to go ahead and make these transparent. I'll make this light gray, and then let's do 0.5 transparency, like alpha thing. And then that should be everything we needed to model in context. We're gonna have to do this motor mounting thing here in a second, but I want to get the rest of these components here. So, okay, let's go to the assembly, and then we're gonna go to insert. We're gonna insert the other end cap, the standoff, the two roller tubes, and click OK. And then I'm gonna edit my group here and add. Oh, I don't want to add that to the group. That's constrained. I want to add that to the group. I want to add the standoff to the group and the two tubes. And then what I want to do is just take the standoff and just copy it and just mate in the two locations it needs to go, like that. And then just double check here that, yeah, there's like a nice gap between these two. Min distance 80 thou, plenty of space. Okay, so then that is that. So we need to cover, so a few more things we got to do. So we got to do the motor mount block, we got to do the bearing retention, and we've got to do the shafts that go in here. So let's go ahead and do that now. So okay, so let's do the shaft first, then we'll do the bearing. We'll do the opposite order I mentioned. We'll do the shaft first, then the bearing retention, then this motor block. So okay, I don't think we need the context for this. So bearing retention will be pretty straightforward. Basically, all we're gonna do is I'm just gonna put some holes right next to where the bearing flange is, and then what you would do is you would just put a rivet where the flange of the rivet is like slightly overlapping the bearing, and that just keeps this bearing from coming out. Now, normally, if this were a rigid structure, I would not do that, right? Because obviously this bearing can't come out normally. This bearing cannot escape because this end cap is keeping the bearing in, right? If the bearing wants to come this way, this end cap has to move that way along with the tube, along with this end cap, and then this end cap is then pushing on this bearing, so it's kind of keeping everything constrained. However, when you build an intake like this, where you've got polycarbonate side plates, there's so much flex in this structure that a lot of times the bearing can pop out anyways, so you do need to positively retain the bearings. So if you're doing this in like aluminum or something, you don't need to have bearing retention, but in polycarb you usually do. Um, Now the one thing to understand is that the rivet tail, like the back end of the rivet, the little mushroom part of the rivet, will stick out. They can stick out as much as a quarter of an inch on this side. So if there's something you're trying to clear, using a rivet like that might not be your best option. You could also, there's a lot of different methods. You could use a screw head and like tap into the polycarbonate. That works okay. Those tend to come loose though. You could do a little um, like um, a little like 3D printed plate that gets riveted or screwed together. You could do nut and bolt. There's like a lot of different things you could do. The rivet one is kind of the simplest and fastest as long as you're okay with the kind of back end of the rivet sticking out on this side. If you didn't want something to stick out on this side, but you still wanted to use a rivet, you could go the other way and you could put a washer here and rivet through the washer. The only thing is that means you've now got a lot of rivets sticking out on the inside, and that basically is going to mean you're probably going to need to increase this gap between this pulley and this bearing because that rivet will interfere with the pulley flange probably. So a lot of different things you can do. That being said, the height of those rivets is typically less than a 16th. So we're okay to do what we're planning to do without increasing this gap. All right, so let's go ahead and just do that real quick. I think I'll just put 2 holes in. So I'm just going to go here, going to go on this plate, add a sketch. I'm just going to go ahead and project this, make it construction, make this line. This and the center point of the circle will be midpoint relationship. And then I need, this is a 1.225, I believe is the OD, the bearing. And then the hole is going to be 0.196 like usual. I'm gonna use the whole feature for this, but I need this construction geometry here. And then I want these to be tangent to each other. I want the hole to be like tangent to the edge of the bearing. This has a horizontal constraint, I think. Oh, it doesn't. Why is this fully constrained? Something's off here. Something's constrained to something it shouldn't be. I don't know what's going on. I'm just going to delete this and start over. I want this to be not at a horizontal angle. And then that should be midpoint. There we go. I don't know what that was constrained to. I couldn't see it. Okay, so then the other thing that I want is a little easier to see from this side. I want this to be like equidistant from this hole. Like I want as much space between this and the standoffs as possible. That'll make installation easier, and it also reduces the risk of like cracking through these holes if all the holes are really close together. So the way that I'm going to accomplish that, I think, is I'm just going to do a line here and here like that. And then these will be construction. And then I'm just going to keep them selected and hit equal, and it makes them equal length, which means equal distance, right? So I think that's a little trick that I think I like in this situation. And then I'm going to do the whole feature, 196 like usual, select these 2 points. That'll be good. Obviously, this is a very thin wall between these two. However, because it's only thin in this little area, and then as soon as you move away from this area, you have a lot more material. This is a totally acceptable thing to do. Also, in reality, a lot of times what we do with these anyways is we don't even necessarily cab them in. We just drill them after the fact. We just put the bearing and we just put the drill up against the bearing flange and just drill. That's a totally acceptable way to do this as well. That being said, if you're taking the time to CAD it in, then you can let the router cut these holes for you. Okay, so let's go ahead and do the shaft now. So we need to switch back to our context, and just going to use the shaft generator. It's going to be 1/2 inch hex. It's going to be thunder hex. It's going to be bolt and washer retention method. It's going to be up to face. So the origin is going to be in here. It's going to be that circle, and then the end face is going to be this ghost of the bearing here. Now the hex is not aligned. That's, a little annoying, but it's totally okay. Can we actually do this? Yeah, we can. Okay, so you can actually align it. If this is at some weird angle, you wouldn't necessarily be able to align it, but that's okay. And then because the spacing here and the end cap here is the same, it's the same shaft over here. So we just need to model it once. And then this should probably have a part number as well because it's a custom cut shaft, right? We would just cut this on a lathe or with a saw and just tap the two ends. No problem. If the shaft ended up being a little bit too long, that would be okay. And then basically what we do is we put the screw in the back here, and that and it threads into the shaft. And then the shaft essentially becomes part of the end cap because you're essentially bolting the shaft to the end cap through this bolt here. Now, when we originally created this end cap, I made this a 196 hole. Basically, the new shaft that Rev is going to be carrying is it's also the same. It's the same rounded hex profile, so it's compatible with anything you're using here. But it has a tap size for a number 10 screw, which is nice because RoboChargers and a lot of other teams try to standardize around number 10 hardware. But right now, Thunderhex is forcing you into using 1/4 inch hardware for that stuff. So basically, if you used Rev shaft here, you could use a number 10. That being said, this shaft generator is just generating with a standard Thunderhex profile, which is tap for a 1/4 20. I think we're just going to go ahead and adjust this hole just to make it compatible. It doesn't really matter either way. Obviously, RoboChargers has 1/4 20 and 1032 hardware on hand. We try to stick to 1032 as much as we can, though. So we would probably use a number 10 screw here. That being said, I think I'm just going to go ahead and keep this compatible with this shaft generator for the purpose of the class. Okay, so I also want to edit the material. It creates its own 7075 material, but I want to use the built-in one just because I don't see any reason to use that custom one. I'll make this dark gray color as well. And then I wanted to edit. Do I need to hide this? I need to hide this. I want this to be 0.261. That's like a loose clearance for a number for a 1/4 20. Could be 266 as well. 257 is close. 261 is standard, and 266 is loose, if I remember correctly, for 1/4 20s. Okay, so then give us a little more room here. We can show the roller again. The shaft is there. So let's go ahead and go to the assembly. Let's insert the shaft. And then we need to add this to our group because it was modeled in place in the part studio. And then I need to copy the shaft over here and then constrain it to that. Okay. All right. So then that takes care of that. And so we have one more thing left to do, and that's to model the motor like standoff block thing. And then basically the only thing left to do after that is just to go through and add all the fasteners and stuff. So I'm going to go ahead and model the motor standoff block, and then we're going to have the one last video part where we have the where we go through and put all the fasteners in, which should be a relatively quick thing. There might also be some spacers too. Although I'm looking at this, I think the answer is no. Yeah, the answer is no. We won't have any spacers because you just put a retaining ring on this, and that's it. So, okay. All right. So let's go back to our part studio here. Go back to our context. once it loads. There we go. All right, so then this motor standoff thing would just be a 3D printed part, and it basically is just we're going to have long screws that go through this into the motor, and it's just going to be basically a round spacer with a cutout for the belt that just picks up all of these holes. So this is a pretty standard part. Most teams do this the same way. Like this is kind of like one of those parts that every team designs the same way, but every team just 3D prints it themselves. To be honest, there probably should be a off-the-shelf version of this, but everybody has slightly different gaps that they like to work with, so it's kind of one of those things that it's just easy for people to 3D print themselves as well. Okay, so what we're gonna do here, I think I'm just gonna base this off of this plate. So I'm gonna do a sketch like that, and then oh, I forgot this is really obnoxious. Always. We'll give it a try. Okay, so then I want these 4 holes. I need access to this geometry, so I'm just going to project these through. Yeah, see, this is the issue. So creating a sketch on a on a um, on a part like this is like on a like context part like this always gives you issues because it won't let you project like onto the surface you're already working with, and it's like I just want that geometry in my sketch no matter what. So I just usually just do a plane, and then I just do an offset of 0, and then I just create my sketch on the plane. It's super annoying to do that, but it just keeps things cleaner. So then it allows me to select these normally and project them so that they're actually part of that sketch, so that when I turn off the context, like I can see where those holes are and stuff. So, okay, go ahead and I need this projected actually, but it's gonna be construction, and then this should be not construction, and it should be co-radial with that. Oops. Equals fine. Co-radial equal, same thing really. Okay, so then what I'm gonna do here is create a circle here and here. And then between those two, those are going to be tangent. Those two are also going to be tangent. And then I'm going to create a circle like this that's tangent with one of them. And then now what I can do is just trim that, that, and that, and that. Okay. And then that is basically our little standoff block. And then we just need to double check that this belt stays inside of this, right? It doesn't hit that. Otherwise, we'd have to kind of configure these holes. But it's good. So we can extrude that, and we'll just do up to face, up to the motor face. That means if we change where this motor is in the assembly, this part will just update. Okay, good. And then we should rename this, give this a part number, and assign the material. It's 3D printed, probably 3D printed out of PLA to be honest, but I'll just make it ABS just because there's not a PLA preset, and ABS is reasonably close. And then I'll set the color to, usually we would just 3D print this in blue. Most of our 3D, we generally do like all of our 3D printed parts in blue just because it's our team color. Okay, then we should go to assembly and then insert this guy, and then this can be added to the group as well because it was modeled in place in context in the part studio. Okay, and then we can zoom in here and see there's like a nice big gap between the belt and the thing, and it should be symmetrical top and bottom. It's kind of hard to see because the standoff's in the way, but get just the right angle, you can see the block here and the belt here, so we're good. Okay, let's give this a once over real quick, make sure I'm not missing anything. We got shafts here. We need to put the bearing in here and on the other side, but we'll do that in the next part when we go through and do all the fasteners. We got the shaft here. I'm not going to model the screw that we put in the side. That's a little bit more work than it's worth usually, and that's generally not printed in, so I don't want to cut the hole here. Although an improvement I've been thinking about for in the future, maybe we do model it in, but I'm not going to go into that for the class. Okay, I think we're good. So, all right, so like I said, in the second part, we're going to go through and add all of the fasteners, and we're going to import these bearings in from McMaster. and also the tube nuts as well that go inside these tubes. I'll show you what those parts are. So I'll see you guys in the next video.